Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning and greetings to all of us. The Honorable, the Coordinator of Doctoral Program of Mathematics Education, Professor Dr. Ratu Ilma Indra Putri MSI, the Honorable, all lecturers and staffs of Mathematics Education Department, the Honorable, our speakers, Professor Dr. Martin Dolk, and also the audience of this general lecture. Firstly, let's say thanks to Allah Subhanahu wa Ta'ala who has been given us His blessing and mercy. And secondly, may peace be upon our Prophet Muhammad Sallallahu Alaihi Wasallam. Ladies and gentlemen, here I am, Fiona Adelia, as the Master of Ceremony, and I will guide this general lecture. Before starting our agenda, let us say Bismillah to start this general lecture. The next agenda is the singing of the national anthem. Please all the participants to rise for the singing of national anthem. Please have a seat. The third agenda is greetings that will be delivered by Professor Ratu Ilma as the Coordinator of Doctoral Program of Mathematics Education. To Prof. Ratu Ilma, time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera untuk kita semua. Good morning Martin Dolk. Good morning everyone. This is a general lecture from Utrecht University Today we have guests from Utrecht University, Associate Professor Martin Dok. So Martin Dok he already well known and has often given general lecture in the mathematics education since 2009, right? Okay. Yeah, 2006, yeah. Today he will provide material about numeracy at school, a representative of undergraduate, master, and doctoral program student already here, and the other one online. There are 91 participants in online by Zoom, and Martin will give a 2-hour lecture. I hope you can be active and participate in this lecture to be fullness, right? Okay, enjoy. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. And the next agenda is pray that will be led by Bapak M. Hasbi Ramadan. For Bapak Hasbi, time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, let us bow our head for a moment, pray to God Allah Subhanahu wa Ta'ala, so that our meeting can be precious to all of us. I will lead this prayer based on the teaching of Islam, and those who are not Muslim, you are pleased to pray according to each of your beliefs. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Hamdan hamidin, hamdan syakirin, hamdan na'imin, hamdan yu'afi ni'amahu yakafi wajidah. Ya Allah, today in this beautiful place, we gather here to bring a meeting, numeration in junior high school with study program of Matematika education, Universitas Sriwijaya. Ya Allah, please make this meeting as a useful science, as a medium of sharing useful ideas, knowledge, and best our experience. May the meeting we organize today will benefit to our life, broaden our knowledge, shine our ideas, and lead us to be a successful and productive person for our nation. Ya Allah, guide and bless our heart and our mind with the light of your guidance. Impart your supreme wisdom in our activities. Help us to speak our mind clearly. Help us to listen to each other, respect to each other, and also love each other, so that we are included to the blessed person. Ya Allah, show us the right path and give us knowledge and strength to perform the good things. Ya Allah, please fulfill our prayer. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Walhamdulillahirabbil alamin. Wassalamualaikum warahmatullahi wabarakatuh.
The next agenda is what we have been waiting for. The general lecture from Associate Professor Dr. Martin Dok from Utrecht University. For Martin, time is yours.
Thank you, Ibu Fiona.
Anytime.
Soon to be Dr. Fiona.
Thank you, Amin.
Can I stand, guys? Yes, thanks. We are talking about numeracy today, and I hope you can show my slides. And for some reason, that is not working. Oh, no, I know why. No. So, I'm from the Netherlands. The country you know is the country of cheese and clocks and tulips and fishermen. So let me show you my fellow countrymen. You might recognize some of your lecturers here. I will speak English. I'm so sorry, but I don't speak Bahasa. Of course, you can speak English, but if you think I'm not 100% sure, say it in Bahasa, and soon to be Dr. Fiona will translate it. If I talk too fast, you stop me. You ask to clarify. It is a conversation, it's not a monologue. So make it a conversation. For the people online, we will use the waterfall. What is the waterfall? When I ask you a question, you take your time to solve it. You enter your answer in the chat box, but you don't push send. You wait. You only click send when I ask you to do that. Why do I do that? So that everybody in the chat has time to think. In classrooms, children immediately might give an answer. What is the effect? Basul immediately gives the answer. You all stop thinking. And that is not what we want in education. We want all children to think. We want to give all children think time. So shouting the answer is not helpful in mathematics education, but it happens a lot, especially here in Indonesia. And what is the effect? The teacher talks to that one child who gives the answer, and all the other children are either not listening or they feel dumb. They don't like mathematics anymore. So that is something we have to change. And we start here today, online. That means we work with the waterfall. So let's test that a little bit. What is mathematics? We are talking about numeracy, that has to do with mathematics. So the question is, what is mathematics? Could you describe what a mathematician is? What does a mathematician do? Can you describe what is a good mathematics problem in school? So think about it for a minute. If you're online, already type your answer in the chat box, but wait. Let me give you a moment to think about it. And guys, you are here, so sorry, I will definitely ask one or two of you to answer. But I also want to see what people in the chat box will say. What is mathematics? Can you give one word? Can you give a definition? Can you give an example? What is good mathematics? In class, I would always want my students to give me a sign like, okay, I've had enough time. Because as a teacher, I'm not the one who decides if you need more time or not. You, the learner, needs to decide whether you need more time. So, are you ready or do you want more time? You need more time, okay. Thank you. So let's talk about it. Before we do that, people online, can you post your answers now in the chat box? Just show us what you have been thinking. So, online people say counting, thinking, calculations, 1 and 2 is 3, the knowledge of regularity, a mathematician is a solver, mathematics is the basic science that builds and opens thinking. Can I ask some of you to give your ideas about mathematics? And feel free to do it in Bahasa. Go ahead. And there is a microphone, otherwise people online will not hear you.
Okay, I think mathematics is way to think. With mathematics, we can think logically, systematically, analytically, and reasoning.
Okay, more people. Don't worry, if you don't say it, I will ask you to say it. So you better do it now. Go ahead.
Thank you. For me, mathematics is a universal language that is used to think in solving the problem.
Isn't it interesting that you study mathematics education and you struggle to talk about what it is what mathematics is? Do you even know what you are studying? So, what did you write down? Can you give the microphone? Otherwise the people online don't hear you.
In my opinion, mathematics is the science of logical reasoning, calculation, and its application in there. Thank you.
So, some people talk about the reasoning, the thinking. Some people talk about the act, solving problems, 1 and 2 is 3, counting, seeing patterns. So it's quite a variety of approaches. There was a very famous book, What is Mathematics? And it's this thick, and even there are definitions, but there are also a lot of examples. And we finish between the two. Now, how do I do this? So, can you remove the chat box, please? Is this mathematics? And online you can show with your hands by showing a hand up or down, or typing in the chat box yes and no, if you think this is mathematics. Oh, was it visible? Yeah. So online, can you put in the chat box a yes and no if you think this is mathematics or not? Let me see some hands here in the room. Show a hand if you, a thumb up if you think this is mathematics, a thumb down if you think this is not mathematics. Show me hands. Everybody. Everybody. Thumb up if you think it's mathematics, thumb down if you think it's not mathematics. It is almost 100%. You say it's mathematics. The people online are a bit quiet. Oh, they raised hands. Oh, I missed that. Thank you. Sorry, guys. So, I think these kind of problems is school mathematics. I don't think this is mathematics. Because, and I will come back to that, what we use here is a student as a calculator. The only thing the student has to do is to calculate. In most cases, the rule is already given by the teacher or by the textbook. There is no thinking involved. And that was what a lot of people, you talked about it, but all the other people too, you talk about mathematics as thinking, as reasoning. Here, this kind of problems, you're only calculating. Now, let's look at those calculations. Could you solve this problem for me in a minute? 2 6/7 plus 2 2/9. Could you solve it? Because I like to see how you solve it. Please, everybody, solve it for a minute. Online, solve it. Type it in the chat box, but don't say what your answer is. And when I say solve it, I don't want to know the answer. I want to know how you do it. So, if you type it in a chat box or you're going to tell me, you tell me what you were calculating. So I'm going to show you the solutions by 2 students, Habi and Jaden. And walking around, I see a lot of you being Habi and a lot of you being Jaden. So let's not discuss it. If you have solved it online, can you put it in the chat box? Let's see if anybody is awake online. Can you remove the chat box? Here is the work, and I will zoom in, of 2 boys. Habi, an Indonesian boy of 12, and he was, at the moment he did it, still in primary, and Jaden, a 14-year-old Dutch boy. And it all started because Jaden had to prepare for a test, and he asked me help. And I looked at the way he solved it, and then I talked with Dr. Puri in Jakarta, and she asked her son, and that is Habi. Now, if I zoom in, not this problem, but comparable problems, see if you see the difference between how the two boys are thinking. And you can recognize if you're more one or more the other in your thinking. The top solution transforms 1 7/15 by saying 1 is 15/15. So I get 22 15s. 5 2/3 is 15/3 plus 2/3 is 17/3. And then I need to go not to thirds, but to 33. So I have to multiply 17 by 11, 187. Huge numbers. Very easy to make calculation errors. Now, the boy on the bottom, 5 2/3, what he says is, I can move those 5 out. If I have to add, I use the different properties, the associative property. 5 2/3 plus 7/11 is 5 plus 2/3 plus 7/11. So I don't use the big numbers. I'm not going to transform that 5. So I only have to look at 2/3 and 7/11. That means that you use smaller numbers, less errors. The boy on the bottom is using all kinds of properties. The boy on the top is a calculator. And if I go back to our problem, 2 6/7 plus 2 2/9, you could say that is 4 plus 6/7 plus 2/9. Makes your life a lot easier. Now, how come that boy on the top exists? Because nowhere in class they allowed him to start thinking. Nowhere in class they allowed him to discuss whether his solution was easy or not. He used a standard algorithm that, according to the teacher, always worked. And it is very difficult if you belong to the top to start thinking about numbers, how to make my life easy. But numeracy is for a whole lot about how to make my life easy. So let's look at some examples, not secondary level yet, primary school. For you, can you solve these problems? And it's best if you have a piece of paper and just do it on a piece of paper. Makes your life a lot easier. Is there paper around? Because a number of people have nothing. Okay, stop for a moment. Just stop for a moment. I want to talk about the first one, because maybe you can approach these problems slightly different. So, when I look at the first one, what most of you do, I saw some people only writing down the answer, what is wonderful, but it's difficult for a teacher then to know what you have been thinking. So in class, if people only write the answer, I would still ask the question, how did you do that? If I say, how did you do that? Most children interpret that, oh, my answer is wrong. But I literally am more interested in your thinking than in the answer. So I definitely, if I say, how did you do that? It is interest, not correcting. That is something, that's a social norm that you have to talk about in your classroom. You have to change that in classrooms. Now, if you do this, most of you do this. 3 and 8 is 11. I have to remember 1. 3 and 9 is 12. 1 more, 13. Or you did 4 and 9 is 13, etc., etc. You put it underneath each other. It is an automatic reflex, and I'm not sure if it is 100%, but I think that almost every Indonesian student is doing this. And I literally don't know why. It is not numerate. It is calculator. So, if children do that, they do something like this. 3 and 8 is 11, 3 and 9 is 12, 3 and 9 is 12, 3 and 4 is 7. I did what you asked me to do. And now you tell me it's wrong? Teachers are stupid. Constance Camille did research about students who use standard algorithms. And in many cases, she said, the power in which the answer is incorrect can be in the thousands, in the millions, without the child realizing it cannot be true. Students who start to think also make mistakes. We all make mistakes. But their answers are much smaller. So if you really think, you would say 3,000 and 4,000 is 7,000. It needs to be in the neighborhood of 7,000. It can never be 7 million. You check yourself with the size of the numbers. And I can still go wrong. Now, if I start thinking, I just want to be sure you know it's wrong. If I start thinking, I do different things. 4,998, yeah, that is 5,000. That's what you do in a shop. Something costs 399,000 rupiah. I say to myself, oh, 400,000 rupiah. If it is almost 5,000, I can add 5,000. What did I do too much? 2. So I go back 2. That is something I can do in my head. It's easy. If I go 5,000 more, 8,333, I have the size of my number. So going to 7 million is not possible for me anymore, because there is an alarm bell in my clock, in my head, that immediately says I did something wrong. If I have it on my computer and my computer says that 7 million, I say, what went wrong? That is numeracy, but numeracy for primary schools. And when you teach in secondary, you hope that your children would come in with this kind of numeracy. At this moment, probably not. So you have to do something about that in your class. This is not the only way. You can think about it like this. I moved 2 from the 333 to the 4,998 using associative property. So I really need to understand what that is, that associative property. That is very important. But now the problem is 3,331 plus 5,000. That is insulting, sir. Go back to a lower grade. You don't ask us that. That's too easy. And numeracy is about making your life easy, partly. So if you think, you can see a lot of good solutions. Now, back to our list of problems. I'd like you to think about those problems, not the standard way. I'd like you to think about it, can I do it in a smart way? When I look at the numbers, would there be a solution that makes my life a lot easier? Let me give you a few minutes to think about that, and then we talk about them.
Boleh sambil diskusi sama teman di sebelahnya, Bapak Ibu? Ya, boleh sambil. Untuk Bapak Ibu di ruang Zoom mungkin bisa diketik dulu seperti permintaan Martin tadi. Diketik dulu di chat room. Padahal undangannya
Can you put in the chat box how you solved 3002 minus 2998? Can you put in the chat box what you did?
Pertanyaan kedua, oke. There's one answer. Oke. Ya Bapak Ibu, untuk pertanyaan kedua boleh diklik jawabannya.
Slowly answers are coming in. That's good. All right. When you looked online, people say, and I saw the same solutions, I do 3002 minus 3000, and then I have to do something with that other 2. Children sometimes think I have to subtract it. They get to 0. And of course, if you think, you know 0 cannot be good. So, can you remove the chat box, please? Yeah, thank you. So, when I visualize it, I could say, I make a jump of 2 from 2998. That brings me to 3000. I make another jump, and that brings me to 3002. Subtraction has 2 meanings. The distance between the 2 points, or removing. And in many textbooks in Indonesia, only one of the 2 has been introduced. So most children think about removing 2998. That makes life miserable, because it's a lot of work. But if I interpret it as, oh, it's just the distance between the 2, it's easy. And so numeracy has to do with the understanding of what an operation like subtraction, of an operation like division, can all mean. Numeracy means that you have to introduce a wide body of mathematics in problems, things. And of course there were more solutions. When I look at 120 times 999, most of you started to think about 120 times 1000. Remove the chat box, please. Thank you. 120 times 1000 is easy. But then I have to remove something. Do I remove 999 or do I remove 120? Now, in the visualization, in the model, you see it's a very small stretch. It is 1 by 120. So I have to subtract 120,000 minus 120. If you just do it in your head, things can go wrong. If you start visualizing, representing your thinking, if you're used to use representations, you correct yourself. So, 120 times 1,000, and then I have to remove 120. That is 119,880. I can do that in my head. I don't need to put it underneath. And $400 divided by 16. If I ask that somewhere, children make a long division. And most children don't know what long division is, and they go totally wrong. And once again, they hate you as a teacher. Now, 400 divided by 16, you can see that as a fraction. Division, fractions are the same. But children don't know that, because it was never allowed for children to start to develop that knowledge. The linkage between the different operations was never discussed. If I see 400 divided by 16 as a fraction, and I wrote it as a fraction, then of course I could say it's the same as 200 divided by 8. It's the same as 100 divided by 4. It is the same as 50 divided by 2. It's the same as 25 divided by 1. And somewhere down the road, something is knowledge. 100 divided by 4, almost all children know that is 25. And that was an easy fraction, and 400 divided by 16 was a hard one. Why? Because we never talk about the relation between division and fractions. And that's a part of numeracy. I can represent it. 400 divided by 16 is, for instance, an area, a rectangle in my case, where I don't know the length of one side. But if I halve that, I have that 200 divided by 8. If I halve that, I have the 100 divided. So in the visualization is also the justification of why you do it. It is helping children to develop an understanding. Almost all Indonesian teachers only use numbers. When I am in a classroom, I never ever see a mathematical model. A model to help children to understand what they are doing. They miss out on helping children. And why do teachers do that? Because they think children are calculators. Children are not calculators. With this drawing, I can now ask children in my class, help me, why is that line that I set on the top, why is that true? Can you talk us through it? Of course, I can draw it differently. Now I lose a little bit of that relationship. Because if I do it in 3 different drawings, I don't really see that halving process. So it's not only that I visualize, I have to visualize it in a way that helps children to build that understanding. 257 minus 139. A dreadful problem. 7 minus 9, everything can go wrong in a classroom. But if I look at it differently, and there are many ways to solve it, I only show 1 or 2. If I look at it differently, it becomes much easier. I can add 1 to both sides. 258 minus 140 is already a lot friendlier. If I represent it, this is the 257 minus 139. I once again look at the distance. This is the 140 minus 258 minus 140. I moved the red arrow, the red bow, the red curve. I just moved it one place. The distance is still the same. If I want to continue, I could make it 268 minus 150. I could even make it 318 minus 200. Equal distance is sometimes a beautiful way to make a hard problem into something easy. But children are not allowed to think about that strategy because the main strategy is putting it underneath each other and subtracting without any knowledge about place value. And that leaves children in a terrible place. They make a lot of calculation errors, and the teacher hates it, the children hates it, and everybody says mathematics is not fun. Numeracy is about allowing you to start thinking about the numbers. You have to look at the numbers, and the numbers tell you something. There was some research by Anne Dowking from Oxford in the United Kingdom, where she asked a lot of people problems like 0.98 divided by 0.79. Hard problems. But she says, I don't need to answer, but I need to know that you get very close to the answer. And people have all kinds of ways to solve that. She asked 40 mathematicians, and 3 months later, she asked the same 40 mathematicians to do it again. 39 of the 40 used a different approach. They looked at this problem because what they had been doing. They didn't look at the problem because they had a standard approach. So the 0.98, you can make it 1. And the 0.79, you can make it 0.8. So it is 1 divided by 8. It is 10 divided by, 1 divided by 0.8. It is 10 divided by 8. 10 divided by 8 is something I can do. That's a good estimate. But you could also sometimes, 0.79 is 0.77, that is 7 times 11. I can go to fractions there. So all of a sudden there are 0.98 is 0.99 divided by 0.77. Hey, that is 9 divided by 7. And so there are many ways to look at a problem like that. And that is what we call numeracy. Not that you are a machine with one approach. No, you look at a problem and you solve it what is given to you at that moment. That's a totally different way of looking at problems. What I say is, when you first look at the numbers, you can make many problems easier. But you have to have the freedom to do that. And models, visualizations, representations help. And when I did the first problem, none of you were making a drawing. And later on, I started to see more people making drawings. Using models, allowing children to develop models, is part of numeracy. It is also part of the question, can you justify what you did? So when students only write down their answer, sometimes that's great. But I want them to be able to say how they did it. I am not interested in the answer. I know the answer. As a teacher, you all know the answer. What you don't know is how your children have solved it. And so if I say, how did you do it? That's an honest question. Because they know you as a teacher cannot correct them because you tell what you really did. If I say, what is your answer, you're immediately scared. Because it's right or wrong. And you know that 7, really? And then he says 8, because he thinks, that is wrong. And the question defines how students respond to you. Ask questions where they really think, oh, he or she is interested in what I was thinking. Not questions where you already know the answer and you're checking them. That changes the dynamics of your classroom. That changes the norms in your classroom. And socio-mathematical norms and the social norms in a classroom are very important. How many dots do you see? And if you're here in the room, you can work with your partner. If you're alone, sorry. If you're at home, you have to do it yourself. Of course, I'm not interested in how many there are. I'm interested in how you do it.
Silakan diskusi bersama teman di sebelahnya, Bapak Ibu.
It's difficult to put in the chat box how you did it. So I'm not going to ask you, but can you put in the chat box how many dots there are?
Untuk teman-teman yang di ruang Zoom, boleh disebutkan ada berapa titik?
Another one. Nice. Yep. Yep. I really like it how people in the chat box, within the limited amount of space that you have, are able to say what they have been doing. Of course, we all agree it's 25. And once again, here, the answer 25 is not really interesting. What is interesting is how you did it. So, I would, when we were in a small group here, I would ask many people to tell us what they did. But let's have a look at some strategies. Could you remove the chat box, please? We saw online some person say 1 plus 3 plus 5 plus 7 plus 5 plus 3 plus 1. And more people did it. We look at horizontal lines because we organize it in groups. And then we can add the groups. That makes our life a lot easier, making groups. And it's a huge strategy that children in kindergarten are already developing. In kindergarten, they are counting. But counting 26 or 45 is difficult for them. So you hope that they will make groups of 5 or 10 so that they can move from counting to skip counting. And that pays off because now you use that strategy of making groups to look at it. But this is not the only way. You can make groups like this. And I see some people nodding like, yeah, that's what I was thinking. Diagonal, sometimes words are difficult. Diagonal lines, and you have lines of 4, and you have lines of 3. And so it is 4 plus 3 plus 4 plus 3 plus 4 plus 3 plus 4. Or it is 4 lines of 4 and 3 lines of 3. Or I look at it this way. I have that triangle 4 times of 3 points, and I have lines of 3 and a dot in the middle. 8 groups of 3 plus 1. Or I do something like this. I make groups of 5. And I have 5 groups of 5. If I was in class and I have been counting all of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 26. Oh, well, 1, 2, 3, 4, 5, 6, 7, 24. You immediately are intrigued by the fact that I don't have to count everything. Children are lazy. Ooh, it looks like you are lazy too. Children are lazy, and to force them, to bring them to the idea of more abstract solutions, laziness is a great motivator. So instead of 3 and 4, I will do 23 plus 44, because there you bring children to the idea I can use group of 10. 3 and 4 they can do on the fingers. 6 times 6, children create 4, they can do it on their fingers. I want them away from finger counting, so I use large numbers. And in many cases, that is just making the problem more difficult, bringing in a constraint, so that you move children to more abstract. And then you get more of these grouping strategies. I can look at it with, hey, there is a 3 by 3 square in the middle, and there are 4 groups of 4 on the side. It's also 4 times 4 plus 3 times 3, but it has a different visualization behind it. So when you wrote in the textbook, it's 4 times 4 and 3 times 3, I didn't know whether you were looking at those diagonal lines or you were looking at it like this. So I need to ask you, what did you do? But a very important mathematical strategy is sometimes I fill it up. So instead of subtraction, instead of addition, I look at it from a subtraction point of view. It is 7 times 7 minus 4 times 6. And I don't think I've seen that one in the chat box. Having said all this, how many dots are here? you understand why I come up with this slide. Because if I do the first one, students have to develop a way of thinking by looking at all the different solutions. And in a class, I would allow students to talk about those solutions. I would not present it myself. By allowing them to look at all the different solutions, they hopefully start to think about what am I going to use next. So by going to a larger figure, I am helping them to think about more generalized solutions. 5 times 5 plus 4 times 4. Hey, the earlier one was 4 times 4 plus 3 times 3. Now you say it is 5 times 5 plus 4 times 4, 4 square plus 3 square, 5 square plus 4 square. Do you think if I go one more row around it, that it will be 6 square plus 5, plus 5 square? I can ask generalization questions, and I will come to that. Four times 6 plus 4 plus 1. Hey, that is one that I also recognize from earlier. If I look at the lines, I can still look at the lines. If that was a solution that was meaningful to me, I can use this solution here too. This is where the 4 square plus 3 square and the 5 square plus 4 square is coming from. And it's a summation of two squares. 16 plus 9 was 25, was also a square, but 25 plus 16 is 41, is not a square. The addition of two squares can be an investigation by itself. In the first one, 16 and 9, I hope that all my children recognize that that also were numbers that came back with Pythagoras. So I can even think about how that relates. I can look at that 5 by 5 figure in the middle, and then there are 4 triangles on the side. 5 square plus 4 times 4. Or I can look at that triangle, again, 4 times 6, and those lines, 4 times 4, plus 1. And again, if you just write down a number or an equation, I don't know what you have been thinking. I need to see these drawings. I can look at this one. In that red figure was my earlier figure. That was the 25. I know it's 25, but I added 4 lines of 4. So it is 25, my old figure, plus 4 times 4. So that idea is something I can generalize. It's the old figure plus 4 times 4. It's the old figure plus 4 times 5. It's the old figure plus 4 times 6. It's the old figure plus 4 times 7. Hey, do I now have the possibility to say, if I go to a site of length n, can I come up with a formula how many dots there are? Can I generalize? N is 4, N is 5, N is 6, N is 7. Can you remove the chat box, please? Thank you. N is 4, N is 5. We talked very shortly about N is 6. But can I go to N is N? Now I'm doing algebra. I started in a counting situation, and now I am looking at an algebraic formula, defining how many dots there are in the case the site is n. My colleague Martin Kind started it much easier, because this is way more your level, not a student level. My colleague Martin Kind started with those shaped, V-shaped bird formations. If you look around, you might see them in flying over. And there is, of course, a lot of biology and a lot of STEM behind why birds do that. But you can also wonder, how many birds are there? And if you are counting how many animals you see, you have to be able to do that quite quickly. And so he asked children, if formation 1, how many birds are there? Formation 2, how many birds are there? Formation 3, how many birds are there? And soon children start to say, oh, it is the wing and another wing plus 1. Or it is the wing and you go to the top one, and it is the other wing, you go to the top one, but now I've counted the top one double, so it is -1. I get a lot of different ways of describing it. Now, then I can talk about how many are in n. Children come up with different equations, and that means that I can now compare those equations. Why are they the same? Because I know they are the same, because we talk about the same flock of birds. But how come you write it differently? 2n minus 1, you have 2 times n minus 1 plus 1. Well, wait a minute. Well, how is that possible? And children will start to explain why they are the same. In other words, children start to explain why different equations are the same. What you have been doing in algebra in the lower grades of secondary. Well, have been doing, maybe are going to do. And so here we see a problem that is introduced so that children can create the mathematics. And once again, the answer is not important. It is the mathematics we are after. So I'm not interested in n and I stop. No, when I know n, that is when the real mathematics starts. And of course, you can add more questions. So if these are perfect formations, and 2 formations merge, and you can find videos of that online, will that be another perfect formation? And when you ask that, children will start to do something, 1 and 4, or 2 and 5, or 3 and 3, or they will start merging certain, but to answer it generally, in our terms, I have to do a formation with length n and a formation with size m. And I have to move that. But at a very low level, where children already talk about in primary school, a formation is always an odd number. So I am adding 2 odd numbers. And children in grade 4 primary school can already say that the addition of 2 odd numbers is even. So the formation of 2 perfect bird formations is never a perfect bird formation. I can do it very formally with algebra, and if I understand it, I can do it with 4th grade mathematics. And you will see, if you really do it, you will see all those levels coming up in your classroom. And some children listen to that and says, oh, of course, it's an odd number. And they have a beautiful aha at that moment. Because they were just looking at the formula 2n plus 1, or 2 times n minus 1 plus 1, that kind of difficult equations, and they don't realize that 2 times something plus 1 is just an odd number. Having seen that, they can now check some of their answers. They are looking at what they are writing, not just writing letters. And so the bottom one is the more difficult formal one. And the top one is an informal solution where the children try to say odd and odd is even. But in this case, they do it with talking about that leading bird in the beginning. And so you see that some children answer the question in the context. They use the language of the context to answer it. And that is the definition of a good context. I need to switch my colleagues at the Freudenthal Institute a couple of years ago created some units for middle school in the United States. Revisiting numbers. Because number sense has to do with the idea of what is numbers and how does it work. And many middle school children don't know everything, and that is what you will see in your classes too. So revisiting numbers is very interesting. And yeah. They start by describing a situation. Your neighbor offers you to pay to be his son's math tutor. You agree, and you set up your first tutoring session with Harvey. Harvey comes to the room, sits down, opens his textbooks, and the problem you see is a crate of lemonade contains 24 bottles. If a supermarket manager brought in 49 full crates, how many bottles did she buy? And you look at Harvey and you say, how did you try doing that? And in many cases, people will say 24 times 49, 9 times 4 is 36, and it goes wrong. But Harvey shows the following table. Harvey used a ratio table. And he wrote this on the paper. And so Harvey looks at you and says, did I do it right? That's that real student's question. Did I do it right? So think about it for a minute. What did Harvey do? Can you explain his solution? Can you help Harvey to see whether he did it right or not. Being able to explain someone else's solution is a part of mathematics. It's a part of the justification and discussion process. Mathematics consists of justifying your approach, looking at someone else's approach, understanding that, and being able to criticize it, add on, or say why it is okay. So look at this solution. Is it okay? Yes or no? Talk to your neighbor if you're here. If you're online and we're watching with somebody, talk to them. Otherwise, think about it for a minute. Is this approach correct? I give you a few minutes. And talk to your neighbors. You are not alone in the world. So the question is, what did Harvey do? Now, of course, you can answer it very at the low level. He used a ratio. But that is, of course, not enough. So the question is, what kind of calculations did he make in his head without really talking about it? What kind of calculations are implicit if I use this calculation, this ratio table? So let me ask someone to explain what he or she has been thinking, looking at it. If you are Harvey and you would have to explain it, what did you do? And when I ask you, you can also do it in Bahasa.
Okay, thank you for the time. I'm sorry my English speak is not well enough, so I can explain to bahasa, my bahasa, oke? Okay? Baik, saya di sini mendeskripsikan saya sebagai Harvey, yang mana saya mendeskripsikan bahwa dia itu bagaimana jika dalam suatu supermarket itu dia memerlukan 49 crate atau kotak. Dalam satu kotak itu terdapat 24 botol. Jika saya adalah Harvey, saya akan memecah 49 crate itu menjadi beberapa kotak. Pertama saya akan membuat dulu, berasumsikan dahulu, oh bagaimana kalau 10 kotak? Karena dalam satu kotak itu ada 24 botol, bagaimana dengan 10 kotak? Oh berarti saya menggunakan multiplication atau perkalian. Bahwa yang di atas itu saya kalikan dengan 10, lalu yang di bawah saya kalikan dengan 10, maka saya akan mendapatkan 10 kotak dan 240 botol. Kemudian saya lakukan lagi sampai ke 49, itu kan berarti ada 40 dan juga ada 9. Sehingga saya memerlukan, oke, untuk puluhannya saya sudah dapat 10, dan untuk satuannya berarti saya bisa menambahkan 5 dan 4. Yang mana untuk 10 itu, dari 10 ke 5 itu berarti saya menggunakan prinsip pembagian, saya mendapatkan 5, dan juga yang juga kita gunakan konsep pembagian yang bawahnya itu saya dapatkan 120. Kemudian itu baru mendapatkan 5, karena saya ingin mendapatkan 9, bahwa saya bisa menggunakan operasi 5 tambah 4, sehingga saya juga harus membuat bagaimana dalam 4 crate itu ada beberapa botol, yaitu 96. Sehingga saya tinggal menambahkan bahwa terdapat 40 crate itu ada 960 botol yang berdefinisi dari puluhannya, dan 9 satuannya saya mendapatkan 216, dan tinggal saya tambahkan, sehingga dalam 49 kotak itu terdapat 1176 botol. Terima kasih.
So, I am allowed to think vertically. 1 crate, 24 bottles, 10 crates, 10 times as much, means 10 times 24. It's a vertical multiplication by 10. But I'm also allowed to look at it horizontally. 10 crates to 40, if I halve it, I split the 10 crates, I have 120 in each. But it might be that the child had said 1 crate is 24, 5 times 1, 5 times 24. I don't know what the child really did. But then, when I look at the numbers, 5, 4, and like you said, 4 is probably subtracting 1 crate. So, subtracting 120, and then if you go to 5 and 4, it is the addition of the 2 stacks that brings you to 9. The 40, probably 4 times 10 crates. Now, in my class, I would like children to make small curves, bows, from 1 to 10, 10 times. From 24 to 240, 10 times. From 10 to 5, divide by 2, 240 to 120, divide by 2. It helps them to think about what they did. It helps me to understand what they did. It is communication. 5 plus 4, you have a bow and then an arrow to the 9, addition, plus. 9 and 40, I added that up. Of course, if you really look at the numbers, if you really understand the numbers, you could also have gone to 10, 50, or 5, 50, minus 1. This is not the only solution. And in class, you might see many children who start to use the ratio table in different ways. The ratio table is a powerful model if you understand how it works. And children need to understand it. And in this textbook, this question is so that children have to really think about how does the ratio table work. So once again, it's not about the answer. The answer was already given. In almost all textbooks, you would stop with the second dot and you would say, how many bottles are there? Here, they give the answer. They take away the mathematics children can do, the calculations, and they go to, can you understand it? It's a totally different way of thinking about mathematics. You children have to get used to it. But I do that a lot. When children have to solve something, I say, okay, so the answer is 41, but how did we reach it? And half of the class think that's the only thing I could say. But after I do that 20 times, they get used to it. And then when I say, hey, what do you think? They often start to explain it. They don't give the answer. They start to explain. And then halfway they say, oh yes, the answer is 41. The answer becomes less important. The argumentation becomes important. That is what they are after here. Now, how does it continue? So the story goes on. The next time you see Harvey, he pulls some notes from his backpacks and says, remembering that problem? Some of my friends did it in a different way. And here is that 50 and 49. Of course, in a class, when you are the teacher, you know, what did you do? And you know already, she did the 50 minus 1. What did you do? And I know that you did the 40 and plus 9. And then I can innocently say, totally different solutions. How's that possible? Or I can say, how are they related? And I want children to be able to explain, yeah, one is going for an addition, the other is going for a subtraction. Yeah, come on, that is the same. 50 minus 1 is 49, and 40 plus 9 is 49. If I was a bit stupid, I would have gone to 100 minus 51. That was a silly, but it's possible, but it's a silly solution. I want my children to be flexible enough to come up with that. And then the book continues. So that, oops. Like I did earlier by showing you Habi and Jaden, here you get Sandra and Hetty. And Sandra, let me see, online you have a perfect view, but here there is a line between the problems that, and I cannot get it right. Yeah, like this. Sandra used the ratio table, 1, 9, 40, 49. What did she do to the 9? We never know. I hope she did 10 minus 1. But maybe she multiplied by 9. We don't know. 10 minus 1 would be easier. Hattie used the algorithm as you probably have learned it in school. And now the question they ask is, how are those two solutions related? And the interesting thing is they are the same. But for a child they are not the same. Because the solution from Hattie, most children don't think in place value. They think 4 times 4, 4 times 2. They lose place value. In Sandra's solution, children think in place value 40 times, 40 crates, 40 times 24. And thinking in place value is extremely important in numeracy. So both have the same numbers, but the mathematics and the understanding underneath it will be different. You learned Hattie's way, correct? You didn't see Sandra's way. And Hattie's way no modeling, no representation, no visualization. Sandra's way has the ratio table as the model. And so in whatever you're going to do, you have to introduce ratio tables. I could, in Sandra's way, of course, introduce N. How many bottles with N? Yeah, 24N. How many bottles with M? 24M. And if I add those two orders, N plus M is 24N plus 24M, or 24 times N plus N. I can use variables in the ratio table. And you can think about it when you do algebra. Is a ratio table a good model here? I'm not going to show you, but in some situations we also use a double number line as a representation, as a model. But important is that you introduce models. And my computer says that he is in need of power, so I'm going to do that. And I show you point 5. So think about how that relates. So while we were solving the power problem with the computer, you had time to think about this representation. And this representation is a different way of writing this algorithm. 216 and 960. So the question is, where are those in this drawing? Well, you do, where's my mouse? 20 and 4. You do, on the top, 40 and 9. And if you now multiply each of those, 40 times 20, 40 times 4, 9 times 20, 9 times 4, you see all the numbers appearing from the algorithm. And so all of a sudden, I can help my students in middle school, the early grades of secondary, to understand all those multiplications they have never understood. But it also opens up understanding of A times B A plus B times A plus B, or A plus B times B plus C, or A plus B times A minus B. All those manipulations of multiplications that children never understand, if they start to understand this model, they start to understand how those multiplications work. And so algebra starts with good education in number. And if your children don't understand number, they will have an extremely hard time in algebra. And that is why in these units we start numeracy for secondary with a good understanding of all the things they never understood in primary. And of course, I can now talk about division. If I have 32 staplers and a large company orders 2,000 staplers, 32 staplers in a box, and they order 2,000 staplers, how many boxes do I need? And you can do that in a ratio table. You do it as repeated addition or repeated subtraction. And now you can talk with students, how does that relate to the standard algorithm? Now, there it comes. That standard algorithm, of course, is a repeated subtraction. But if students never really understand that, they will have problems with a squared plus 4a plus 4 divided by a plus 2. Or the factorization of those. So to talk about all those equations and being able to factorize it, they need to deeply understand how long division works. And this, what is on the board, is something they don't understand. The yellow box is something they understand. In a context, it becomes meaningful. The ratio table is something they understand. And so, starting with all that manipulation of variables, a squared plus 4a plus 4 is, factorize it, is only becoming meaningful if you first have been doing things like this. And that is what I call numeracy in lower grades of secondary. It's shortly before 10, so let me stop talking and let me see if there are questions. Questions here in the audience or questions online. I see the chat box, so if you have questions, put it in the chat box. Questions?
Ya, Bapak Ibu kalau ada pertanyaan boleh. Untuk Bapak Ibu di ruang Zoom juga boleh diketik di chat box pertanyaannya. No questions? Tidak ada pertanyaan? Teman-teman yang di sana mungkin yang cowok-cowok ada pertanyaan? Oke.
Okay, thank you for the chance. I want to ask to the Martin, based your experience, you say that numeracy is about making our life more easy. Okay. Yes, because I make note about the sentence based on, we already did some questions that using so many strategies that we didn't use as usual, like the Sandra's strategies, but you show us that so many strategies that really interesting to do. Best, can you give us suggestion as the future teacher and also I'm as a parent, how to teach our child or our student to think so the strategies can appear not like the standard ways. Because I think it's really difficult to make it. Thank you.
If I look at Indonesian textbooks, there are no contexts. There's no support. What happens is that in an Indonesian textbooks, they give an example and then they say, they don't write it, but they say, follow my lead. Do this. And I looked up all textbooks that I could find about long division, and they were, in their explanations, inconsistent, not explaining every step, and sometimes even wrong. So my first advice is, don't look too closely to the textbooks. Create examples where the children themselves find solutions, where the context is so powerful that the children talk in the context. Because if they don't talk in the context, they don't have the support of the context. Harvey was talking about grades. When he looked at his ratio table, he talks about 9 grades, 40 grades. He didn't talk about 4, what all your children do in an algorithm. He talked about 40. So the context needs to be so powerful that you talk in the context. And then just listen to children. I don't think it's wise to say to children, you need to have 5 different solutions. You need to have 5 different ways of doing it. No. But I have to be open that you do it this way and that you look at it that way. And I have to be so extremely fast that I just look at your work and I say, oh, that's what you did. And I look at your work and I say, oh, that's what you did. And I look at your work and I say to myself, oh, that's what you're doing. And that is very difficult for a teacher. I have to see all the different solutions. I have to anticipate. So if I go back, I'm allowed to do that. So we go back to the first problem. If you have that problem of the crate of lemon drops and the 49, if I know that is going to happen, before I go into class, I already imagine how can children solve it. And in my head, as a teacher, I have several different ways. I know that some kids will do the long division and make errors. I know that some children might go to 50 minus 1. I know that some children will say 40 plus 9. I don't expect it, but children could do 7 times 7. Because 49 calls out 7 times 7. I don't think they do it, but who knows? I will look around. And then I have to think about, okay, so if all those things are there, how can I challenge my children? So if you are doing it with 50 minus 1, what question can I ask you so that you have to think a little further? If you do it 40 and 9, what question can I ask you so that you go a little further? And that makes life very difficult. But it all starts with what the children do. I was in a classroom in Bandung a couple of days ago, and we showed children a dish with 6 by 6 pen pack. Much nicer than in the restaurants here because they are not ordered. No, they were nice in a rectangle, 6 rows of 6 pen packs, or 6 columns of 6 pen packs. And the question was, children in grade 3, how many are there? Now, when I do that, I say to myself, I will see children counting. And I know, when I look at that they will probably count and count again and count again and count again, because they are not certain about the answer. You know you make easy mistakes with counting. I might see children doing groups of 6. I might see children doing skip counting, 6 and 6 and 6 and 6. I might see children trying to do handy grouping, 12 and 24, 30 and 6. Now, with all those children, I need to know how I continue. So if a child is counting 7 times, oh, wrong. And then Ilma is starting to count again, and then I count again, and we have 35, we have 36, we have 37. I need to know what I will say. And I would probably say something like, that's a lot of work. Do you think we can do it differently? And I know that later on there will be kids in class who did 6 and 6 and 6 and 6. And so I can learn from that. The student who was counting can say, that is handy. And if they do 6 plus 6 plus 6 plus 6, then if they listen to kids who did 6 and 6 is 12, so I do 12 and 12 and 12, oh, that is less work. Or I do 18 and 18, 20 minus 2 plus 20 minus 2. Or I did 5 times 6 is 30 because I knew that. So there are all kinds of levels of going further. Now, in whatever you do, you have to think about what kind of solutions are possible. And how is the progression from very concrete to very abstract? And if I know that progression, then I know how to help my children. For a parent, very difficult. Most parents in secondary will not know how to help their children. So it comes down to you as a teacher. It comes down to you as a teacher to predict solutions, to see the progression, and to know how to help from concrete to abstract. And there was another question, because halfway my talk you got the microphone. There was a reason you did that. Say it in Bahasa.
Okay, thank you for the time. I want to ask a question. We know that a student can find different ways to solve the math problem. So as a teacher, how do we decide if a student method is a good one? Should we look at how the method is, or how well the student can explain it?
How do we as teachers decide if his or her solution is a good one? There are 2 sides to that question. Yes, when I look around, I need to know if it is good or not, because I have to make a decision whether I ask you to share it or not. But at the same time, it is not my role as a teacher to say, good, wrong, wrong, good, wrong, wrong, good, wrong, wrong, stupid. It's not my role. My role is to say, how did you do it? How did you do it? How is it possible? Different answers. Oh, I made a mistake. Yeah, everybody could have made a mistake. Where was it coming from? So my role as a teacher is not to tell children it's wrong or it's right. Most teachers do that. You give an answer. I show it in my face. Don't do that. But very quickly looking at whether the answer is right or wrong, asked that we know a hell of a lot more of mathematics than the students. That is why you were anticipating. That is why before class you already have 2 or 3 different solutions ready. Not one, not your solution. No, you anticipate what students might do. Teaching is incredibly difficult, guys. It is way more difficult than parents realize it is. It's also very satisfaction. It's a great job. I've done it all my life. I love it. But it is not easy. And even more important is that as a teacher, if you do it right or wrong, I can say, yeah, that was a mistake, but that was great thinking. And I have to celebrate your thinking, and I have to celebrate your thinking. So I really need to know my mathematics. And if I don't know my mathematics, I cannot teach that subject. And that's, I just repeat it, is an enormous amount of work. I'm sorry. I've been told that I have to stop talking, and I love talking. I hope I was not talking too fast. I now say very slowly, and I did talk very fast earlier. Sorry about that. Thank you very much. Really enjoy being a teacher, because it's a wonderful job. Thank you.
Maybe we can take a photo together, a group photo, for the documentation. Okay, maybe we can take it with the online participation. So on my count, 1, 2, 3, smile. Okay, thank you. That's all for today. Oh. Yeah, sudah. Okay, please open the camera for the online participant who has not opened the camera yet. Atau silakan dibuka kameranya Bapak Ibu di ruang online Zoom. Sepertinya hanya itu yang buka. Langsung aja. Oke, kalau begitu kita foto sekali lagi. On my count, 1, 2, 3, smile. Okay, thank you.